Okay, so I'm going to talk a little different topic. I'm going to talk about Epstein zeta function. Epstein zeta function. So it's some kind of naturally generalization of Riemann zeta function. And we have some nice properties, some nice similar things to the original Riemann one. And my goal, my mission is going to be defining this, making sure it's well defined so we have some nice convergence, and proving some functional equation, very similar to the one we have originally. And also, of course, I will connect these things with what we learn in the course. So, definition, we'll take Q to be positive definite quadratic form. So Q is going to be a quadratic form. I will deal with this as is a matrix, but it's just abusing notation, but it's of course the same, more or less. So we define for a complex number with real parts bigger than n over 2, this Epstein zeta function associated with this quadratic form to be 1 over 2, then the sum of all non-zero points in this lattice, z to the n. 1/2 in some books, there's no 1/2, so it depends a bit on the book we're using. This is because it will give slightly different functional equations. So in this case, I want a nice one, so I will just choose 1/2 here. Of course, we recover for dimension 1, n equals 1. We get Q is just, okay, this is just a point. So this would be Q to the minus S, Z, like this is the original Riemann zeta function one. And then Q is just the matrix Q for dimension 1. So naturally, we need to get this in some way. So first lemma is basically that this is well defined. It has some nice, it's absolutely convergent for, real part greater than n over 2, and then is uniform convergence in each compact. Okay. So to prove this, I'm going to use some lemma, which I'll write here because I don't want to use that space. So this lemma is about the number of points in some lattice defined. So it's basically which is inside this ball of radius r. And the lemma says this is of this form, satisfies pi n over 2 gamma 1 plus n over 2 r to the n, and then it has some wait, why am I writing this? This is r n minus 1. Okay. So I will use that to prove this. But the first thing, so another notation I will use to say this is basically saying n of r is, I will say this is kind of bounded. I will call this bounded, but this actually means this in absolute value is less or equal than some constant than this in absolute value, basically. Now we come here. We'll call sigma real part of S. Yes. And now, since we have a positive definite, we have some kind of nice properties of Q. So we can actually bound our Q between these two things. Yeah. Okay, this actually we can take those constants to be some kind of eigenvalues of Q as a matrix. Yeah, for all x, of course. If we do this, we actually want to recover this expression. We want to make sure this is bounded by some things that we know it converges, of course. So now what do we have? Just see this the other way around. Sigma x2 is qx sigma 1 minus okay. Just notice that when we want to look at this expression, this series, the nature of this series is the same as the nature of just taking. How do I write this? No, basically we only need to deal with the real part. That's what I'm trying to say. That's the only interesting thing for the convergence. Because
on the right hand side of this inequality and also on the left hand side.
This is an inequality?
No. So the absolute value of x to squared, this is not, because you're taking qx to the minus sigma, right? So
yeah. Oh. Yeah, thank you. Okay. So the nature of this is basically nature of this series. And this, we can view this a bit differently. We can do this, it's called group by radius trick. So we will see this as kind of growing disks from 0. So we can write this as the sum from m equals 1 to infinity. And now using that notation, it's going to be n of m minus n m minus 1, m to the minus 2 sigma. Okay. I'll call this am. And basically, am is, of course, number of points in this lattice with radius between m minus 1 and m. So, yeah, another way of seeing this expression, is basically summing over all these radius, all these modules or absolute values. So m minus 1, and then x minus 2 sigma. Okay. Yeah. So notice we have this inequality, which will help us bound what we want with this am. So m minus 1 x squared m minus 1 minus 2 sigma. Okay. This is because, okay, just take that from in here. The radius is between m minus 1 and m, so we turn this around. Okay, so once again, the nature of this, of the series, just taking series summing from m to 1 to infinity, is just the sum of this. Okay. So basically what we want And now we'll use this, our theorem, our lemma. To actually see what shape this thing has. This has some constant, which is that one, times m to the n. So this is nm minus 1, just using that lemma. You can put this together. N plus some O m minus 1. And then this is going to be just n times something, O m minus 1 times this constant. So actually this am, using that notation, is bounded by mn minus 1. Or just some O, say. Okay, so this is what we want. Our series is just basically of the same nature as this is mn minus 1. So with this, gets mn minus 1 minus 2 sigma. Of course, this only converges if this is less than 1, minus 1. Yeah. So converges for sigma greater than n over 2. Okay, so this is absolute convergence. I'm gonna see if I have time to do the other one. No. Okay, there's it's quite simple to do uniform convergence. You just take k to be inside here with this property. Compact, you just use Weierstrass m-test, and it's quite clear. It's quite easy, but just don't have time. Okay. So now my main theorem, is analytic continuation. And this theorem is actually quite big, so I will not prove everything, especially some residue results, which is not quite interesting, but the expansion they give is quite big actually. So this theorem says we can prolong, we can continue, analytically continue or expand, I don't know, this function to all C except one single pole, one simple pole at. It's the same as we have with Riemann zeta function, basically. Note that Riemann zeta function, the simple pole is at n is at s equals 1, but it's for n equals 1. But we have this 2s. That's why it's that thing. Okay, the theorem actually says the residue. I'm not going to write it. I'm not going to prove it as well. But we have this. We define this kind of complete Epstein zeta function this way. Okay, so the functional equation that prolongs analytically this function is, in terms of this general or complete Epstein zeta function, determinant of q to the minus 1/2, and then we just invert n over 2 minus s. Okay, and we actually also have part of this theorem is this incomplete gamma expansion. Which gives an expression of this complete Epstein zeta function in terms of another function which I'm going to write here, which is called the incomplete gamma function. So this is kind of definition slash lemma 3. So we define g of Sx to be x to the minus s gamma of Sx, which we can write in this integral form, ys minus 1 e to the minus xy dy, x positive. This is the incomplete gamma function. T to the s minus 1 e to the minus t dt. Okay, and the lemma says, we'll say basically, lemma, this is entire in S for x fixed. Okay. Basically, this theorem also says we can express this function as that gamma Sx, or that actually that g, in some big way. So we have this formula. Okay, this is the determinant of Q as a matrix, of course. Plus 1 over 2. Now we're summing over all non-zero points of this lattice. And now we have G S by Q of x plus Q to the minus 1/2 G n to minus S by Q minus 1 of x. And then this. Okay, I will prove this if I have time. I don't think so, but.
You can also read off the residue from that, right? So
Yeah, exactly. So we can read the residues from here, and we can see that it will have a pole, simple pole at this point, and this point will not have the simple pole because this is coming from the gamma function.
yes, so the completed one will have the pole as equal to 0, right?
Yeah, the complete one, yes, but not this one,
yeah.
which is the one we're interested in.
So what is Q in your notation, the absolute value of Q?
Is the determinant of the matrix. We see
Representing
the quadrangle, yeah. We also have some numerical results. We can compute this from here as well. At this point, we have minus 1 over 2 for Epstein, just recovering this from this formula. And we will have these non-trivial zeros. No, these trivial zeros, the same as the original Riemann zeta function on the points where gamma is not defined. Gamma is 0. Gamma is, what am I saying? No, gamma is not defined, so to cancel this for k natural. Okay. Yeah, what I want is to prove that. So I'm going to erase this proof. So in this proof, I will use our old friend Poisson and his summation formula. Very nice. Okay. I'm going to write this as a lemma here. Lemma 4, also slash definition. We will define for this theta function to be the sum all lattice points. Here we don't take out the 0. We will do it later though. Qx for t0, for t greater than 0. The lemma will say, which is basically a functional equation for theta, but it comes from Poisson's summation formula. Lemma says, so theta of qt is q minus 1/2 t to the minus n over 2 theta q minus 1 t minus 1. Okay, t minus 1 is just 1 over t, is the same. This is real. Do I have space? No, I'm going to prove it here. Proof of lemma 4. And then we will go to that big guy. So I will use Poisson summation. For a specific function, we will take f of x to be e to the minus pi t, and then this is q of x, which I will just write like this. This is how we see q of x, where q is this matrix. This is like matrix multiplication. Okay. Poisson summation says basically this is a Schwarz function. This is equal to the sum of Fourier transform of f. So we'll compute the Fourier transform of this guy. Here the one I'm using to make that formula true is this definition, f of x e to the minus 2 pi x to ty dx. Okay, so of course, if I take f to be this, actually theta is this, like summing f over f. Yeah, precisely. So f hat is just replacing f with our guy, f pi t x t qx e to the minus 2 pi y x t y dx. Okay, here I'm gonna cheat a bit. This is actually some known result. You can Google this on whatever, on Wikipedia. See, this is kind of some multivariate Gaussian, so we can pretty easily, we'll say the Fourier transform is given. Otherwise, I don't have time to do the big stuff. Q minus 1y. Okay, so now, actually theta, which is this sum, is the sum of this, and this is constants, c n minus 2, minus n over 2, and then if we see here, this is basically definition of theta when we put the summation inside of q minus 1 and then t minus 1. It's just y instead of x, t minus 1, which is this guy. Okay, so this is lemma 4. So I'm going to begin the proof of theorem 1. I will only have time, unfortunately, for the functional equation, which is actually the important thing. So we will use this fact that for a bigger than 0, we have that the integral from 0 to infinity of t to the s minus 1 e to the minus pi t is just this. This is just from the definition of the gamma function. So we have, this is actually how it is defined over there. We can sum over all non-zero x. This is from the lattice of this integral t to the s minus 1 e to the minus pi t q of x. Just looking there. And now we will exchange this using Fubini. T s minus 1, and now sum non-zero x e to the minus pi t q of x dt. Yeah, and this is almost our theta function. We just have removed 0 here. So we can just recover it. Now it's theta. And then we subtract 1, which is what we get at 0. Yeah. Now we use our lemma. Inside. So we have absolute value q, or determinant of q, 0 to infinity. We have t to the s minus 1 times s minus 1 minus n over 2, q minus 1, t minus 1 minus 1. Okay, this is just, let's write 1 over t. Because now we're going to do a change of variables. We'll call u to be 1 over t. So we have q to the minus 1/2. And this will give, so first we would change this around, but we will have, in dt, we will have minus u to the minus 2. So we'll have that minus, we will just keep this like this. Now we have u to the n minus 2 minus s minus 1, because we have u squared. And then this is the rest, du.